Hey everyone, my name is Zhi-Xuan or Zhi-Xuan. I'm a PhD student at MIT and I use they, them, or she, her pronouns. I'm excited to present her paper, Modeling the Mistakes of Boundedly Rational Agents within the Bayesian Theory of Mind, which I worked on together with Arwa Ellen Curry, Gloria Lin, Joey La, Vikash Bansinga, and Josh Tenenbaum. People routinely infer the goals of others by watching their actions over time. As this well-known video shows, we can do this from a very young age, as young as 18 months old. In fact, as you're watching this video, notice what happens. The adult pursues a very strange and suboptimal plan. Indeed, you could say that the plan just failed. And yet, the child's able to infer what the adult probably wanted, and it's a recognition of this failure that leads the child to offer assistance. The question then is, what explains this rich and flexible capacity for mental inference? How are we capable of inferring the goals of others even when they fail to achieve those goals? Well, let's look at how some prior work has attempted to answer this question. In an influential paradigm called Bayesian Theory of Mind, Chris Baker, Rebecca Sachs, and Josh Tenenbaum posited that our inferences about the mental states of others can be characterized as Bayesian inverse planning. That is, we model other agents as rational planners that act efficiently to achieve their goals, and then compute the posterior of an agent's goals given observations of their behavior. In experiments they ran in this 2009 paper, they found that this sort of model correlates highly with human goal inferences. But is this model able to account for an agent's failure to achieve their goals? Well, if you examine it a little more closely, it does make a weak assumption about how other agents might not be perfect. In particular, it assumes that agents may choose actions noisily, selecting actions that tend to minimize expected future costs according to a Boltzmann or softmax distribution. And this Boltzmann policy, or Boltzmann agent model, has come to be a de facto standard in both Bayesian Theory of Mind and the related literature on inverse reinforcement learning. However, I think we have reason to suspect that this assumption might not be enough. For one, it seems implausible in large environments that humans are capable of calculating expected future costs for all possible states in order to compute a Boltzmann policy. For another, this only captures suboptimality at the level of our actions. But what about higher level cognitive processes, such as plans or goals? To address these limitations, our hypothesis is that humans intuitively understand that others commit mistakes at multiple levels of decision making. This includes mistaken actions, as discussed, but also misguided plans that fail to achieve our goals, and even mistaken goals, that is, confusion or conceptual errors at the level of goal formation itself. We can formalize this hypothesis by specifying a Bayesian model of a boundedly rational agent as a probabilistic program. The agent has an initial goal, but at every time step, it has some probability of confusing that goal with a semantically similar state, or perhaps recovering its original goal. The agent then plans to achieve that goal, but in a boundedly rational manner. In particular, the agent doesn't form a complete plan from the start, but instead plans only some steps ahead, executes those steps, then replans as necessary. Replanning in this way is less cognitively demanding, but can also lead to suboptimal or mistaken plans. Finally, the agent executes its plan. However, due to execution error or motor noise, the agent may sometimes execute a random action instead, that is, a mistaken action. These actions causes changes to the environment state, and an external observer receives potentially noisy observations of that state. Given this overview, let's dissect the model and its component mistakes a little further. First, mistaken goals. While this might sound like an odd concept, consider that semantically complex goals, perhaps baking a cake to a particular specification or spelling a word, might lead to confusion or memory errors. Is it fiery or fiery? We model these errors by assuming that the goal pursued at each time step has some probability of being corrupted from the intended goal or being corrected from the erroneous goal. Next, mistaken plans. Imagine playing this game of Sokoban, where you have to push all the crates so they end up on the red dots. One approach would be to make a complete plan entirely in advance. But given the difficulty of this problem, that would be extremely cognitively demanding. Instead, when faced with problems like these, we often form partial plans which just extend a few steps ahead, interleaving execution of those plans with additional planning. This reduces computational cost, but can lead to mistakes due to the failure to plan ahead sufficiently. For example, in Sokoban, you might find yourself pushing a crate into the wrong corner and no longer being able to retrieve it. We can model this process using the probabilistic subroutine shown on the left. At every time step, we only continue planning if the existing partial plan does not extend to the current time step, or does not say what to do in the current state. Otherwise, we simply return the previous plan. If we do continue planning, we invoke a partial planning procedure with three major components. The first is the search budget, which specifies how much computational resources to devote to additional planning. The second is the planning algorithm itself, which specifies a high-level strategy for computing a plan. The third is the planning heuristic, which guides the planning algorithm in searching for a good plan. We model the planning budget as drawn from a negative binomial distribution, encoding the assumption that spending a lot of cognitive resources in planning is unlikely, but so is spending too little. We model the planning algorithm itself using a probabilistic variant of A-star search, capturing the intuition that humans often plan by thinking ahead from their current state. The search algorithm can be seen animated on the left in a gridworld domain, where red dots correspond to the states considered during search. Combining this with the planning budget gives a partial planning algorithm, where search goes on until we use up our budget, at which point the algorithm terminates and returns a partial plan to the most recent state considered. These partial plans are shown in blue on the left, which the agent executes before starting to plan again. As for the heuristic which guides A-star search, we model this in a domain-dependent fashion. In domains involving spatial navigation, one might use an optimistic metric like Manhattan distance or maze distance while ignoring the presence of obstacles. In other domains, one might use a more general heuristic from the classical planning literature, which estimates the number of steps remaining to the goal by ignoring certain problem constraints. Finally, let's look at mistaken actions. People may not always execute actions as intended. For example, we might walk a step further than intended past our destination, or might drop something that we're holding in our hands. We model this by assuming that agents usually execute each action as planned, but occasionally execute another action at random. So once again, that's the overall agent model, which accounts for mistaken goals, plans, and actions. I'll note briefly that we also tested legent models, each of which removes the modeling component associated with each category of mistake. So, fixing the goal, G-legend, optimal planning instead of partial planning, P-legend, and noiseless actions, A-legend. Having specified the agent model, we hypothesized that humans perform Bayesian inference over this model. For such a complex model, of course, exact inference is intractable. So we instead approximate the observer's posterior by using a particle filtering algorithm, sequential inverse plan search, the details of which can be found in our earlier NeurIPS paper. To validate our model, we conducted experiments where we elicited goal inferences from human observers as they watched an agent interact with an environment, sometimes optimally and sometimes suboptimally. Given the complexity of our model, suboptimal trajectories might admit multiple interpretations. Was that a mistaken action or a mistaken plan? As such, we designed trajectories to make some mistakes seem more likely than others. These trajectories were designed within two domains, a gridworld puzzle called Doors, Keys, and Gems, and a blocks world environment where an agent spells out words out of letter blocks. These domains exhibit the compositional structure that humans encounter in daily life, making them tractable to plan in, but also complex enough for interesting mistakes to arise. Now I'll show a couple of illustrative results. Watch this agent and try to guess which color gem it's trying to pick up. Notice that the agent exhibits a suboptimal plan, backtracking to pick up the key in order to reach the red gem. Our model accounts for such planning mistakes because we assume that agents may not always plan fully ahead. Its inferences closely match average human judgments, in contrast to the Boltzmann agent's model, which only accounts for action mistakes. Across all similar backtracking trajectories, we find that our full model correlates highly with human judgments. This is in contrast to the P-legend and Boltzmann models, neither of which account for mistaken plans. Now, let's consider a different kind of mistake. Take a second to figure out what the agent would have to do to reach each gem in this environment. Yellow is trivial, blue is a little harder, and red takes some thought. Got it? Now watch what happens. So I think most people watching this would probably say that the agent was trying to reach the red gem, but got stuck because it didn't realize it needed 2 keys and not just 1. Again, our model accounts for this inference because it allows for the possibility of myopic plans, unlike the Boltzmann agent model, which attributes all missteps solely to action noise. And looking at a correlation plot, we see again that our full model correlates more strongly with average human judgments as compared to models which assume perfect planning. Moving on to the block words domain, let's see another example of a mistaken plan. So that was a little surprising. It turned out to be power, not cower. We designed the stimulus to exhibit a subtle form of backtracking, under the assumption that people might sometimes stack one block on top of another without realizing they need the block at the bottom. Let's watch that again. So it seems like the mistake here might be due to a failure to plan ahead, but it turns out that in this example, unlike previous ones, our full model isn't actually more similar to humans than models that account only for action mistakes. And the reason is that we only backtrack for 1 or 2 steps, which could also be explained as correcting a mistaken action rather than a mistaken plan. And so across all stimuli in this category, we end up not seeing a significant difference in human model correlations. While we were hoping to see more of a difference, we think it illustrates the real-world difficulty of disambiguating mistakes, and we find it promising that both mistaken planning and mistaken action are viable explanations here. In the future, we hope to design additional experiments to better elicit the distinction between plan and action mistakes in this domain. Finally, let's see an example of mistaken goals. Watch as this agent stacks lettered blocks, and try to guess what word it's trying to spell. Let's watch that again, just in case you missed what happened. Did you manage to guess pair midway? If so, you're like our other human subjects, who accounted for the possibility that words might be misspelled, an instance of goal confusion in this context. Our model was able to do the same, assigning pair as the most likely goal, once its misspelling was observed. Looking at the correlation plots, we see that our full model is most similar to humans across all trajectories exhibiting mistaken goals. All other models are much less correlated and exhibit much more goal uncertainty relative to humans. And overall, average human judgments correlated highly with our model, and more strongly compared to Bayesian and baseline models. We think these findings provide considerable support for our hypothesis, indicating that it is important to model errors at multiple levels of cognition and action to build an intuitive theory of our boundedly rational minds. Of course, many open questions remain. For one, what kinds of mistakes do humans understand beyond the 3 explored here? Prior research has also modeled mistakes like false beliefs and time inconsistency when inferring the goals or preferences of others. Other cognitive limitations abound. Which of these do humans intuitively apprehend, and which do we not? For another, given the complexity of these models, how do human observers rapidly and tractably infer the goals and mistakes of others? Our prior work suggests that by assuming others are boundedly rational, the inference problem is made easier for observers, because they can perform online approximate inference over goals, plans, and mistakes, instead of exhaustively considering all possibilities in advance. How well do these approximate algorithms explain inferences and potential inference mistakes made by individual humans? By exploring these questions, we hope to build an even richer theory of our boundedly rational minds. With that, I'd like to thank my co-authors once again, and I'm excited to hear your questions.